Uranium is a chemical element that occurs naturally in the ground and is represented on the periodic table by the symbol U, with an atomic number of 92. This indicates that every uranium atom contains 92 protons in its nucleus, making it one of the heaviest elements found in nature on Earth. If you were to hold a piece of pure uranium metal, you might be surprised by its weight. It is extremely dense, roughly 19 times heavier than an equal amount of water. This remarkable density is part of what gives uranium its significant potential as a source of energy. The story of uranium's discovery is quite intriguing. It was first recognized in 1789 by the German chemist Martin Heinrich Klaproth, who was studying a mineral called pitchblende, which is now known as uraninite. He chose the name uranium in honor of the planet Uranus, itself only discovered a short time earlier. Despite this early identification, the true importance of uranium wasn't understood until much later. Throughout most of the 19th century, uranium found use primarily in the production of decorative glass and ceramics, as its compounds could create a striking yellow-green glow. At that time, its radioactive properties were completely unknown. This changed in 1896 when the French physicist Henri Becquerel left uranium laying near photographic plates. After some time, when he came back, the photographic plates turned black. It was an important clue that uranium was emitting a new kind of radiation that influenced the white photographic plate, which we now call radioactivity. This unexpected discovery marked the beginning of research into radioactivity, a field that was later advanced by Marie and Pierre Curie. From a chemical perspective, uranium is a silvery grey metal, but its most notable characteristics come from its behavior at the nuclear level. Its atoms are inherently unstable and can undergo radioactive decay. Uranium exists in multiple isotopic forms, with uranium-238 and uranium-235 being the most significant. Isotopes are versions of the same element that share the same number of protons but differ in their number of neutrons. In naturally occurring uranium, uranium-238 accounts for roughly 99.3%, while uranium-235 is present in a much smaller proportion of about 0.7%. Despite its scarcity, this U-235 isotope is the thing important for nuclear energy because it is fissile. This means that U-235 nuclei can split when they are hit by a neutron, releasing a large amount of energy as a result. This process, known as the scientific concept of nuclear fission, forms the foundation of how nuclear reactors generate power and how nuclear weapons function. And this is where uranium enrichment comes into play. Uranium enrichment is the process of increasing the concentration of the uranium-235 isotope within a sample of uranium. Enrichment works by separating isotopes based on their slight differences in mass, even though they are chemically identical. One of the most common modern methods uses gas centrifuges. In this process, uranium is first converted into a gas and then placed into rapidly spinning cylinders. As the cylinders rotate at extremely high speeds, the heavier uranium-238 isotopes are pushed slightly more towards the outer wall, while the lighter uranium-235 isotopes concentrate closer to the center, gradually increasing the proportion of uranium-235. This process can take months to years, and the result is uranium that has a higher percentage of uranium-235. Low enriched uranium, typically containing about 3 to 5% of this isotope, is commonly used in nuclear power plants, while highly enriched uranium, consisting of 90% of this isotope, can be used in nuclear weapons. Uranium is thus not manufactured. It is extracted from the earth, most of it in countries such as Canada, Australia, Kazakhstan, and Namibia, and then purified to a high enough level of U-235 required either for use in nuclear power plants or in more highly enriched forms for nuclear weapons. When it comes to nuclear power plants, the amount of energy released from the fission of a single uranium atom is extremely small, but when countless atoms split at once, the total output becomes immense. Even a tiny uranium fuel pellet, roughly the size of a fingertip, can generate as much energy as 1 ton of coal, 150 gallons of oil, or 17,000 cubic feet of gas. This is what makes uranium so significant in modern energy production. In nuclear power plants, uranium is formed into fuel rods that are precisely positioned within reactors. As fission occurs, heat is produced, which is then used to create steam that spins turbines and generates electricity. This process enables nations to produce large quantities of power without relying on fossil fuels, making uranium a key element in addressing climate change. At the same time, this form of energy remains controversial, largely because it results in radioactive waste that must be securely handled and stored for thousands of years. And as explained, uranium's story also includes a more troubling side: the nuclear weapons. In the 1940s, during the Manhattan Project, researchers learned how to exploit its fission capabilities to build atomic weapons. The bomb dropped on Hiroshima in 1945, known as Little Boy, relied on highly enriched uranium as its fuel. Click the video on your screen right now, and I'll explain another everyday mystery you've wondered about your whole life but never thought to look up.